All right, good morning, students. So this is the final lesson in Chapter 12. We're going to finish out with earthquakes, and we're going to learn how to use these seismograms here and how to couple this information with page 11 to do something a little more complicated with figuring out epicenter distance. Instead of just using travel times for epicenter distance, now we're going to use arrival times for epicenter distance. So the first thing we have to understand is that on a seismogram, it'll always give you the P and the S wave arrival time. Now here, I've done a good job of labeling it for you. So this one's, really straightforward. The P wave arrived at 11:01 a.m. and the S wave arrived 11:05. So that's a 4-minute difference. So that gives us what's called the difference in the arrival time. The difference between the P and the S wave arrival times can give you an epicenter distance. That's right. So we have to use this 4 minutes here for this particular seismogram. We have to use the 4 minutes and page 11 together to calculate or to figure out an epicenter distance. So how do we do that? Well, let's just do some practice, right? So for seismic station A, you have to figure out what's the difference in the arrival times. And that's going to be, well, here's 8:20. Oh, that's you. That's 8:20. Ha ha ha. Anyway. And this is 8:21. And over here is 8:30. So 8:30 minus 8:21 is 9 minutes. That's, the first difference in arrival time. Again, we're just practicing doing these. The next one is here's 15, 16, 17, 18, 19. So 8:19 minus 8:26. Right? You find that difference, it's 7. These are really, really straightforward. In the future, they might get a little more complicated, but for the most part, this is kind of what we're talking about. Here's the last one, 8:16, 8:21. A difference of 5 minutes. That's just some examples of how you find the difference in the arrival time between two seismic waves, the P and the S wave. All right, and here are the steps, right? This is the steps to finding the epicenter distance using the arrival time difference. So first, you do what we just did. You subtract, right? P, S and P wave. We got that as 4 minutes. All right. Now what you have to do is you have to break out your page 11, and you need a small piece of scrap paper or any kind of edge of anything, and you're going to mark off the 0, and you're going to mark it up to 4 minutes. Now, why 4 minutes? Well, that's our difference in arrival time. So whatever the difference in arrival time is, you always mark it up to that point. So there it is. I've marked it off. You can choose to use the edge of the paper, or you can bring the paper down a little bit and actually make 2 marks. It's up to you. Now, here's the fun part. You have to then move the piece of paper so those 2 marks meet the P and the S wave line. You see how I did that? I've lined it up. I've moved this paper up in a way where now the P and the S wave lines meet that, those tick marks I made. And that's it. From this point, you just read down. So you take this, you follow it down, down, down. Oh, there it is. It's 2,600, 2,000, 2,200, 2,400, 2,600. That's it. That's your epicenter distance. You can even just draw a line down if you want to draw a line down. That's your epicenter distance. All right, so that's the more complicated way of finding the epicenter distance. In the event that the word problem you're given does not give you travel times, it may give you arrival times only. All right, and here's the last thing. We cannot do this, obviously, because this next part we can't do, unfortunately, because we don't have the tools that are at in the classroom. So I'm just going to show you what to do. You can check it out. Just follow along. I'm also going to post a video of Mr. Rankin showing you how to do this. He made a video a while ago. I'll post that too so you can check it out. So the whole point of doing all this is to actually find the epicenter. When we find this epicenter distance, that only tells us the distance from the recording station to the earthquake itself. It doesn't tell us the exact location though. So what you have to do is you have to use the epicenter distance you just calculated, and then you'd have to do that 2 more times with 2 different seismographs and 2 different seismograms. But anyway, here's how you find, or here's how you start plotting this stuff. So this is now mapping an epicenter distance. You have to take your safety ruler and you have to align it. So this is a safety ruler, and you align it along the x-axis. You can see how I have the 0 on the the 0 on the ruler is on the 0 on the x-axis here. And you're gonna have to believe me on this one, but this part of the ruler actually moves. It kind of moves, it kind of slides back and forth. So what you have to do is you have to align, it's really hard to see here, but you have to align this part of the ruler. There's like a little triangle here. It's kind of hard to see. You have to align that with 2600. So you would physically move this entire thing down to where 2600 is. You would just, you physically move that slider to 2600. That's actually what this says right here. Move the slider to the calculated epicenter distance. In this case, 2600. You would move it. Lock the ruler. Unfortunately, those old rulers, we don't have those anymore, and they weren't very good anyway. So you actually can't lock it, so you can ignore that. All right. So here is just an example. It's a map of the United States, and what we have on here is 3 seismograph locations. These are the 3 locations, just random locations that I just randomly chose, where the data is coming from. So let's say that seismogram data, that 2600 kilometer data, came from seismic station A. Let's just say that. What you would do is you would place your safety ruler over, this little O part here, you put it over the actual location. You'd put your pencil inside of this little hole here, and you put your finger over, so while your finger is on the circle part here and your pencil is in here, you kind of move your pencil around and it'll make a perfect circle. That's how that works. Place your finger on the rotating circle here, hold it down, place a pencil inside the slider right here, and draw a perfect circle. And it would look just like that. So just so we can appreciate what this circle is, this circle tells us every possible location that the earthquake could have happened. Because again, just to remind you, I'm just going to go back really quickly. According to this data, which we're going to say came from seismic station A, the difference is 4 minutes. We calculated the distance is 2600. So that means that when we draw this circle means that the earthquake could be anywhere along this circle. The earthquake could have originated on any location along this circle. Well, that's not very good, right? Because there are essentially an infinite number of points or places where the earthquake could have came from. So it's not very helpful. In order to get the exact epicenter distance, you have to do the same thing 2 more times at 2 different seismic stations. And you'd be given data about that, right? That's how you would do it. So I just drew in, again, I'm making this up. I'm just showing you an example. let's say seismic station C has a really big epicenter distance. That's another circle. And let's say seismic station B has a small epicenter distance. Well, you can see where the epicenter is. It's where all three circles come together. And what you would do is you would place an X there, and that's the true epicenter of the earthquake. So this is actually called triangulation. And triangulation is precisely why you can go on your phone right now. You can go on Google Maps or whatever you use, and you can look at the blue little dot on Google Maps, and it'll tell you where you are right now. This is how location-based services work on your cell phone or anything on a GPS. This is how GPS works. Your cell phone basically is sending out information to cell phone towers. The phone and the cell phone tower know how long it takes for the signal to go back and forth, and it's basically the speed of light. So by knowing that time, it knows the distance, and if there are 3 cell phone towers around you, at least 3, it can triangulate your exact location. And that's basically how location, works on your cell phone. It's the same thing. It's called triangulation. So a minimum of 3 seismic stations are needed to triangulate the epicenter location. All right, that's it for today's lesson. There's a test wizard on this, and that's your last test wizard. There'll be a review assignment. We'll play a quizzes game, and then we'll have our test coming up soon.